So this project is a project that we conducted in Emerson Lab, and the genesis of this project is thinking about buildings. First of all, buildings contribute significantly to climate change through their embodied and operational carbon. And we think that, because of that, we have an opportunity to really reduce and target how we design and operate buildings and make a big impact. And as we transition to timber cities over time, some of the newest research suggests that we can really reduce that impact by up to 77% over business as usual if we start to transition to more timber in our built environment. So that's an opportunity that we think demands thinking about expanding how we use mass timber in buildings to not be just structural frames, floor systems, but also in the enclosure. And we started by a WIG grant a few years back where we were looking at an all-wood building that had a mass timber enclosure. We had some funding to be able to perform some infiltration testing on that building. And we were really interested to see how well that enclosure performs because of the monolithic nature of these panels. And our hypothesis was that this was going to perform better than a light steel framed enclosure. Also, that thermal conductivity of wood. So we wanted to test this building doing a whole building blower door test, but some of the issues there were, just unique conditions such as roll-up doors and other penetrations that really wouldn't give us the data that we expected. We did do a test anyway of one space where we were able to tape off certain areas, and we noticed that there were some conditions that were intriguing, such as air moving between the lamella during pressurization and depressurization, and at some of the joints, not all of the joints, where there was a half-lap condition and a butt joint condition. So that got us to propose a study that was funded by an ARS grant through TallWood, where we could specifically look at the mass timber wall assembly and that joint condition in a controlled setting to be able to understand how does this actually perform for infiltration under pressurization and depressurization conditions. Here are the joints that we came up with. The half-lap joint was taken straight out of that building condition, as was the butt joint. And then we added a spline joint condition, and we added MPP and CLT, where the previous field test was a CLT building. And then we threw in sealant versus no sealant. And here's actually kind of the whole list: weather barrier versus no weather barrier, and looked at all those different conditions together in a controlled setting. You can see the panels. We had those milled based on those specifications. Some of those panels were, after they were assembled with the sealant, you see that on the right, what that looks like. And then we created a testing apparatus that was also made out of MPP and had a monolithic air barrier coating on the interior. So this was a custom designed 8-foot by 8-foot apparatus where we could mount those panels into that chamber, pressurize the chamber. And we pressurized it versus depressurized it because you might see we've got let's see if this pointer works. Right here, we have a little party fogger to be able to smoke up the interior and confirm that there weren't any leaks around the perimeter once we pressurized that. And those two sides were fixed with neoprene gaskets, and then that 8x8 assembly sat in there and got constricted to those edges with compression boards with also gaskets, and we confirmed that that had a good seal. So here you see Dale Northcutt in our lab, doing some different variations on this test. You've got, we have a Henry's sealant that we're using with a 1/4-inch bead for the sealant. We used a Suprema WRB that was coming out of that project that we tested in the field. So you're probably wondering, what did we get? I think we presented this a few years ago, talking about getting started, and here's the results. These are preliminary findings that we're working to get published, but the findings across the different panel types suggest that they perform very well. And if you look at the scale, this is air leakage per meter of joint length. And so very, very low air leakage at 75 pascals. This is cubic meters of air leakage per meter. There was some difference based on whether you added a sealant versus no sealant. There was difference, as we suspected, between the MPP and the CLT. The MPP is more monolithic with that resin, and so it performs slightly better. And there was a little bit of difference based on the joint type. The butt joint and the CLT performed better than the other two conditions. But overall, these performed very well. And when you put that, I'm just going to show a couple images of the CLT before I put it in context for you. The CLT, because of the nature of the way that's laminated, there were potential pathways for air to kind of move into the inner thickness of that section and communicate, whereas the MPP was more monolithic. And so that's why it likely didn't perform as well in the half lap and the spline, whereas the butt joint had that full thickness that was touching. So it seemed to perform a little bit better. However, when you put that in context, this is air leakage per wall area, and at 75 pascals for commercial buildings and 50 pascals for residential. This performed, all these assemblies performed, this is an air barrier test. And so these were performing like an air barrier. And even without sealant, they were performing exceptionally well. When you put it in context of the assembly leakage requirements by the ABAA, they're well below that limit. So they performed extremely well. And then passive house, we threw the passive house standard on here because most of you probably know passive house and the stringent requirements for infiltration in passive house. So at 50 pascals, this is what passive house would require for air tightness when you look at this for the whole building. And here's where our assemblies performed in this range. So we're very excited that even though there was slight variation when you zoom in to these assemblies, they overall perform exceptionally when you just look at the performance of these joints, as these panels are very monolithic. So that tells us that we are actually going to get ready to do another test once Judith will probably talk about, well, she will talk about the panelized house that we're doing, and we're going to do a whole building infiltration test on that. And we'll have a chance to get some more data coming up. But the short answer for the question you may have had, how do these perform? Exceptionally well. So with that, I want to thank the project team, which included Dale Northcutt going to Emerson Lab quite frequently to run all these tests, Jason Stinson, and then Davis Whalen is a student in Portland who's been working on the paper for us right now. All right.